find another resource. So everything, the whole mechanism, the whole deal should happen in 50 milliseconds. So this is something which is never in existence in MPLS, right? The third thing is a bidirectional mechanism, because if you look at it, most of the LSPs, as I said, are unidirectional. But in the case of TPE, you want to have bidirectional. So point A to point B, you want to have A to B as well as B to A. So bidirectional LSP is by default, and those could be signaled or they could be associated. So you set up, then you associate, saying that these two directions are associated together. Then, not only that, you want to interoperate with existing MPLS technologies. You do not want to come up with whole new MPLS paradigm and say that this is the MPLS TP for you. So you want to work within the constraints of MPLS TP. Then whatever the protocol extensions you are doing, it has to be transport agnostic. So you cannot define for ATM, this is the transport technology, for Ethernet, this is the type you need to use. So irrespective of what payload you're carrying, everything should remain the same. So if you see, I put MPLS TP within MPLS. So what it conveys is MPLS TP is not a new technology. It is stripped off MPLS. So in other words, you took away a lot of things which were added in MPLS by taking away the control plane requirement and all that stuff, and made a vanilla kind of MPLS. So MPLS TP is a subset of the whole MPLS. By the way, if you look at in any of the MPLS TP RFCs, you don't find any new thing defined for MPLS. So there is no protocol extension as such. Most of the things which were defined were how to make the MPLS work for transport requirements. That's pretty much it. So what exactly is being solved by MPLS TP? It is primarily replacing the traditional TDM networks with packet switch networks, and at the same time providing the same set of needs and the wants of transport networks, and providing bigger pipe tunnels. Then it also, the primary thing is you are bringing down the OPEX and CAPEX. How do you bring OPEX and CAPEX when you are introducing whole new technology, asking for whole new tool sets, and in order to maintain MPLS TP? So how it is doing is the whole MPLS TP paradigm or the technology should fit into the existing transport technologies. So if you are having the TDM based NMS or EMS, the whole thing should fit into that. So you should be the network administrator should be able to set up the paths just like he used to set up all of the SONET SDH paths. So that means the interface should be able to provide the similar interface in order for you to set up, and underneath how it sets up is nothing of a concern to the administrator in a sense. The OEM capabilities, all of the OEM capabilities present in the existing transport network should be in existence in MPLS TP as well. Then fault detection and the recovery mechanism should be the same, means it should be the same requirements. And path computation and also the SLA requirements should be provided as well. So if you look at it, there are three different categories you could categorize what MPLS TP is bringing to the MPLS. Is from operations perspective, previously it was all control plane driven, now it is NMS driven. That means NMS should be able to drive the whole establishment of LSP, to maintenance, to troubleshoot and all that stuff. Then in the OEM category, you're in the packet accounting and all those metrics, including SLA metrics, were not mandatory in the packet or IP MPLS networks. Now it is mandatory in MPLS TP networks. So if you take an MPLS TP LSP, you should be able to find out the whole count packets with specific intervals and the response times and all that stuff. So those things are all mandatory. Of course, the reliability, it should be able to support all types of topologies, linear, ring, shade mesh protection, with all the protection schemes. Then switchover should be there. Then also the requirement of 50 millisecond switchover. Any questions thus far before we jump into some of the tools? Okay, either you're not able to follow or you're totally understood everything. Okay, I take it as you understood everything. Troubleshooting MPLS. So I have explained this, what are the problems in MPLS networks. Some of the things which I haven't covered, mentioned were there is a problem which is called black holing, where you see packets being sent from the ingress router, but you never see them out the egress router. So that means they're being black holed somewhere. So that means that they're getting dropped. They could be dropped either because there was no path from some path in between has broken. It could be due to control plane and data plane mismatch, like control plane could have signaled saying that you take this path, but data plane might be doing forwarding, maybe forwarding based on its own forwarding table, which is not in sync with control plane, and somewhere the whole thing broke and the packets were being dropped. Then the other problem which I explained is if you disable MPLS between penultimate hop and ultimate hop, you may not be able to figure out whether MPLS is enabled or not, because the packets could be, routed from ultimate to penultimate hop to ultimate hop, but they're not, the MPLS is not really enabled. So in some cases it may be passing, some cases it may be failing. And some of the MTU issues, which is very, very critical thing in MPLS networks, because you could have hierarchical LSPs and the MTU size could be decreasing, and if you're trying to send a larger packet, it could be dropped, or you could have a defragmented packet and you may have out of sync issues. Then, of course, as I explained, ECMP problem, which is a tougher problem to solve. So the primitive debugging methods were just use ICMP to verify 2PE route, the path between 2PE routers. So that means you're emulating the data packet by sending ICMP. That means ICMP packet will be a label packet and it will be sent. The other mechanism to use is WRF-aware ping. So you actually specify a ping packet to take a specific LSP by specifying that WRF. Then you could actually go and figure out in each of the device using CLI or SNMP or whatever by checking the forwarding tables and see whether forwarding table entry exists or not. Then you could check each of the interfaces, saying that whether this interface MPLS is enabled or not, then check the MTU size and all that stuff, right? Then you could also see whether control plane protocol is existing and it is working, and there are various mechanisms to do that as well. So what is the problem with ICMP ping? See, ICMP ping, yeah, you could encapsulate, have the ICMP packet encapsulated and send it just like a data frame. But what if the LSP between P2 and P3 is broken, right? So usually what happens is the P2 will pop the labels and it punts and it does a IP lookup, and if IP route is existing, it forwards the packet to PE2. Most likely the IP route will exist. So that means ICMP will not indicate an LSP failure between P2 and P3. then as I said, it cannot verify ECMP paths as well. So ICMP you cannot really use in all the cases or majority of the MPLS cases. In the case of VPN aware ping, so this is the next level of debugging. So it actually emulates the VPN traffic. So you encapsulate the packet with the same label stack of VPN. And in this case, in this example, if the LSP between P3 and PE2 or penultimate hop and ultimate hop is broken, you cannot detect in that case as well, because it will just forward the packet and you'll get the response, but the LSP is actually broken. So those corner cases you cannot figure out with LSP ping, with VPN ping. Then it also cannot do ECMP, and it cannot detect control plane to data plane mismatch. For example, if control plane says you take Ethernet 0/0, but the actual data plane or the forwarding entry is Ethernet 0/1, so there is a mismatch, and the packet is going with a different label, and you cannot really identify that. So MPLS OAM. So this is the actual MPLS OAM which I'm going to talk about. This deals with how to measure, how to perform various OAM operations on these MPLS networks. And so it should be able to do proactive as well as reactive based OAM. So proactive means I should be able to continuously check a given LSP before I realize there was a breakage. And reactive is, if there is a breakage, I found using some proactive tools, the subsequent action of how do I know next what to do. In other words, how do I figure where exactly the problem is, what is the problem, and what is a quick fix I could do, right? Then it should have the ability to, diagnose a specific error and convey the message. So that is another critical thing. Yes, we could diagnose, but how do I aggregate multiple errors into single error so that is what it is? Or how do we derive based on multiple? Because you could have like timeout, you could have like label mismatch and different kinds of errors at the same time, but how exactly you can figure out aggregating all those errors. Then of course provide a carrier class toolset, not just a simple toolset. So what is LSP ping? LSP ping is based on UDP based mechanism, and it is to detect different LSP failures, label mismatches, control plane to data plane mismatch. Then also it actually figures out what exactly the problem is, and it can tell you what the problem is, and also it tells you the MRU, not just the MTU. So MTU is what is the transmittable size, whereas MRU is which actually tells you what is the payload size. So you could have like 4 labels or 5 labels. So MTU will only account for all of, but you could, on that LSP, you could have like 3 labels. So MRU will tell what is exact payload you could send with those 3 label stacks. So that way you could figure out how to deploy my network based on the hierarchical LSP model, so which is very, very useful. Then it should be standard, because you need to interoperate with multiple vendors. If it is single vendor, I'm okay, I could design whatever I want. But if I have mix of different devices, I should be able to interoperate with different vendor devices. So that means it should be a standard. And it should be able to verify all different type of MPLS FECs. So it could be IPv4 LDP FEC, or it could be IPv6 LDP FEC, or it could be TE, or it could be BGP, or it could be pseudowire or anything else. So I should be able to verify each FEC type and determine the problems, whether proactive or reactive. Then of course it has to do multicast as well, not just unicast. So the function is to work just like ICMP ping. So we do not want to have a totally different tool set. We just want to extend the existing ping, but add extensions to that so that we could perform just like how we used to do ICMP ping. And you should be able to specify what FEC and TTL options and all the how to encapsulate label and all that stuff. Then when you do that, when you issue that command, the packet should be encapsulated accordingly and sent from point A to point B. The primary requirement is that unlike regular packets, the OEM packets cannot leak into customer networks. This will cause multiple issues. One is security issue. Customers could, folks could misuse by, emulating the OEM packets and sending a DOS attack or disruptive packet attack into the customer networks. So that means you have to terminate no matter what at the egress of the network, MPLS networks. It cannot get into the customer networks. And the response packet should convey all of the details, what it's supposed to tell you. And the other thing is the packet cannot be routable. The main reason is if it is routable packet, if there is an MPLS failure, most likely in majority of the vendor devices, the packet will be processed at the upper layer. If it is an IP packet, then IP processing will happen and the IP route lookup will be done. And if there is a route entry, it automatically routes. So that means you will not be able to find out there is an MPLS failure. So the packet cannot have routable IP address. So what it can verify, so these are, as of now, these are the different FEC types which were defined. Not necessary that this is the FEC types only. There will be more FEC types which gets added as and when new technologies get developed. So as you can see, it pretty much covers the length and breadth of the FEC types. So LSP constructs, there are two types. One is request packet and the response packet. And within the packet, you should be able to specify what FEC it is. And the packet should be able to be encapsulated with the same exact label stack as the data packet. For example, if I'm sending from Vancouver to San Francisco and there is an MPLS LSP from Vancouver to San Francisco, when the data packet is sent from Vancouver to San Francisco, it will be encapsulated with label, let's take 20. So when I send OEM packet, the OEM packet also should have label 20 because this packet should go just like any other data packet. So it cannot be a separate packet because the behavior, if you encapsulate with label 21, the behavior could change and it may not really able to test the exact label path. Then the packet should be able to convey the interface information, so you could actually verify interface information. Then, of course, different label stack and other stuff. And this is the response codes. So as you can see, if you look at ICMP ping, right, when you do ping, the response you get is timeout or a bang sign, which means it has received, right? But in the case of LSP ping, it is not just one value. You have n number of values. So if you take, for example, number 3 is the return code you see, that means if you receive, when you send an OEM packet and you receive response code of 3, that means the response is sent by the egress router. That is the far end. But if, for example, an intermediate node has sent, that means you are doing like TTL3 or something out of 22 hops, you may receive number 8, where it says label switched at stack depth. So that means you're terminating at hop number 2 or 3 based on what label or what TTL hop you specified. So it is not an egress of the FEC, but it is a transit device which is label switched. And it also tells in the written subcode saying that to what stack depth. You could have like 5 labels, but on that hop it is doing only 2 labels, 2 labels were popped or something like that. So it is switching at a stack depth of 2. So even the subcode, it is called RSC, is called return subcode, will tell you what is the stack depth it is switching it. And if there are errors like DSMAP mismatch where you are expecting the packet to receive on interface A, but you are receiving on interface B, that means there is a mismatch of the path. So you may receive number 5, and if there is no label entry, you may receive number 11 and those kind of things. So it gives complete information, not just whether connectivity exists or not. So the label encapsulation will have, in the case of IP encapsulation, you have IP encapsulation along with MPLS encapsulation. So these are the default values, like in the case of TTL, you have 255. And for the case of IP encapsulation, IP TTL will be 1, and that's a UDP destination port. And the source address and the destination address is always local host address. The reason is, if it is popped at intermediate router, it will not be able to IP forward or IP route. Rather, it will be punted so that local host will only process that packet. And this is the reply, much similar. For lack of time, I will pass through. And this is the downstream mapping. This is one of the TLVs. This is the older version. That is a newer version. Newer version is supported because the LSP, originally when we designed, we always assumed the same FEC type from point A to point B, but you could have like a tunnel model where the label stack could change. So we came up with much extensible model, but both conveys the same. So the primary thing which it conveys is when you, in the echo request, you send saying that this is the downstream information. That means the very downstream router, I know what is interface information, what is the label stack of the downstream router. So when I send the packet, I should be able to put that payload in here and send it there. And on the receiving router, it validates whether it is the information it received in the payload versus the actual interface information and compares. And if it is okay, it sends back the subsequent downstream router information so that every hop you could verify for the downstream information. So you could verify label stack, you could verify interface information, you could verify MTU, you could verify MRU, and you can also query the multipath information. For example, from intermediate router 1, I have 6 paths. So that means in the multipath information, I'll have 6 TLVs saying that these are the different type of information. So that means 6 downstream TLVs. I'll package and send it back to the source saying that you can, in order to verify, this is the information. So that if I want to have, out of 6 paths, I want to verify 1 path, I know how to get to 1 path because the router which is sending that information, the 6 path information, will tell you this is how I do the hashing. So if you format the packet with this so-and-so encapsulation, you should be able to hash onto that specific path. So this is what I was explaining. You could send the downstream router information and the receiving router will send back after verification. So like that you can validate each of the hop all the way till the end. Similarly, traceroute uses this deep downstream information. So in traceroute in regular ICMP, you just send a packet to each hop and each hop will respond back. In this case, we send to each hop along with the downstream information, so you not only send to the downstream route or each hop in the LSP, you actually validate each of the router's information and send the response back. So it is much heavyweight than what you experience with the ICMP trace route. So ECMP troubleshooting, which I wanted to cover a little bit. So ECMP, how I'm going to do ECMP troubleshooting? Like in this simple topology, right? I have paths from PE1 to PE2. I could take P1, P2, P3, or I could take P1, P4, P3, or I could take P1, P4, P5, right? So there are 3 different paths I could take in order to reach PE1 to PE2. So, but how I'm going to verify specifically P1, P2, P3? I want to verify only that path. I don't want to verify all of those paths because I just want to make sure those things are working. So first, PE1 will send a request with this downstream information. This is only snipped information, not entire information. Just for the context, I put it a little bit. So the bitmap is the one which is used to identify the pool of addresses. So in this case, let's take, I use 4Fs, which is like 32-bit. Then P1 will receive that request, and it processes that request and tells that there are 2 paths from P1 and the bitmap. So I have 2 TLVs. The first bitmap is Ethernet 0. First path is Ethernet 00, and the second one is Ethernet 2/0, and the bitmap is 00FF, and bitmap for the second one it is bitmap FF0. So what exactly is this bitmap? It is not like some ad hoc number I choose. So what I do is when I receive on P1, when I send this from PE1, when I receive on P1, I receive a bitmap of FFFF, right? So each bit corresponds to 127 address. So in this case, the starting address is 127,000. So that means in a bitmap of 32, I have all the 32 addresses available. That means 127,000 to 127,00031. So all the 31 addresses I should be able to be used by P1. So on P1, it queries for each of those 127 address and the label stack to figure out which hashing will it goes on to Ethernet 0/0 and which hashing goes on Ethernet 2/0. So it figures out the combination of all the source address, in this case destination address is each bitmap address or 127 address, and the label stack, and it queries. So once it figures out, okay, these addresses goes to 0/0 and these addresses goes to 2/0, it combines and forms another bitmap, say like that. So in this case, I simplified saying that FF and 00FF, but usually it could be random based on how it does the hashing. So next one, PE1 will send a third request because the Ethernet 0/0 has 0FF, so it sends with 0FF. So on P1, it automatically goes to, because I send with TTL2, it goes to P2. So now P2 is receiving because that's how the load balancing happens. And P2 will respond saying that there is only one path and all of the addresses will hash on to Ethernet 0/0. Similarly, in the next subsequent request, PE1 will send to P3, then P3 will send it back, then PE1 will send to the TTL4, then it automatically goes P1, P2, P3. So it takes only that path because I have verified at each hop. So similarly, I come back and verify each of those hop. I took a simple example of depth first algorithm. You could employ depth first, or you could employ different algorithms, but I choose a simple algorithm from explanation's sake. And so you have to query each hop in order to figure out what are the equal cost paths exist and what hashing my label stack plus addresses and interface information and other things will take. That's how I query. So this is the ECMP based trace route. So it is very complex, but what you're getting out of it is you should be able to map out your whole topology. You should be able to verify your whole topology. You should be able to verify a specific path in the whole topology. Then you can also troubleshoot any of the problem in the whole topology. And this is not just the theory part. This is actually in working. This is deployed and widely used in majority of the customer large network devices. Like one of my customers, they're having 800 PEs, and they were actually, and each it's fully meshed 800 PEs with 8 ECMP paths, and this works perfectly for them. So, and it requires a little bit of horsepower, but there are multiple ways you could do. You could do proxy-based model. You could buy a bigger box and use it, or you could buy a smaller box, dedicated box, just to do a proxy for you, and you could do all those techniques. So the ECMP is good, but unfortunately not LSP types support ECMP. Like traffic engineering do not support ECMP, then some of the VPNs do not support ECMP. So most likely only IPv4 LDP is in existence supporting ECMP, but things could change in the future. So, but this technology is extensible, this tool set is extensible, nothing is stopping from it to perform those things. But these are the set of FEC types and what tools in existence supporting each of those FEC types. So this why I put as separate for the pseudowire FEC is it is little bit different. In the case of pseudowires, it is not running natively. It uses a control channel which is VCCV. So LSP ping is extended for VCCV so that you could actually verify the pseudowires. And this is very, very useful because in this case IP is not present. You could be running just a pseudowire or TP-LSP. You should be able to run verify the pseudowire. So if the IP is not enabled, you cannot really use all the IP-based tooling like ICMP ping and all that stuff. So you have to use LSP ping for that, and this is or BFD to verify that. And there are different type of pseudowires. You could signal pseudowires dynamically, or you could establish statically, and you could stitch pseudowires dynamically, or you could stitch manually as well. So signaling both automatic and manual, and stitching automatic and manual for multi-segment pseudowires. So BFD, I'll give a simple two-slide overview. BFD is a very, very simple, lightweight mechanism to do liveness detection. So that is CC, continuity check. So you keep rapidly doing keep alive kind of thing, and you should be able to figure out whether the particular interface or path has liveness or not. It is the inverse of ping. Why I say that is, ping is you send a request and you expect a response, whereas BFD works opposite. You negotiate between, when you establish a BFD session, you negotiate between point A and point B, saying that I'm going to send you packets within this time. So that means within 10 milliseconds, you should expect a packet from me. And the other side could tell this side saying that, okay, 10 milliseconds is tolerable, so you keep sending 10 millisecond interval packets. So then once it receives acknowledgement, point A will keep sending packets under 10 milliseconds or at 10 milliseconds. By any chance, if the packet is not received within 10 milliseconds, that means there is some problem. So it assumes there is a breakage. So sending packets is like you expect because that's how you negotiate. But if you don't receive, that is considered as a failure. So that's why it is inverse of ping model. And you could establish two ways. One is synchronous model where you signal saying that point A to point B one session and point B to point A another session, and each could be at different time intervals. And there is loop back where like you just send a packet and it will loop back to you. So that means you are establishing just a loop back session. So there are different modes of operation, and people have come up with UFD also, unidirectional detection as well, because in some cases that is very, very useful. And it is a typical hello protocol. It is also designed to use UDP, or even if IP is not there, it uses UDP format. In some cases, it need not use UDP format, but it is also designed to work in non-IP mechanism. And it is supporting all majority of the MPLS LSP types, and it is supported at IP level also and even transport level. So it is very lightweight. So you could argue saying that, hey, if you have BFD, why do I need LSP ping? Or you could argue, if I have LSP ping, why do you need BFD? So these are not two competing protocols or two competing mechanisms, but rather these are two different types complementing each other. So the way some of the customers actually deployed is you use BFD for faster detection. So because you could run in even to the level of microseconds, you could run very fast BFD to detect failures. Once you encountered failure, it automatically triggers an LSP ping thing, and once LSP ping detects a failure, it triggers route trace, then so on and so forth. So the hierarchy model was built around BFD and LSP, and they never compete in a way, but rather they complement in many ways. And BFD is primarily designed from point to point. There is a way being developed to deploy in multi-point networks also, but that is still works in which is happening right now. So this is what I explained. You have two different ports, one to negotiate and one to exchange data packets. And you could negotiate the rate between A to B and B to A, and both could be asynchronous and need not be synchronous, or you could design in such a way that it could be synchronous as well. So I have covered most of the points here. It is the de facto OAM protocol which is used to trigger any faults, so that the subsequent action like switchover for FRR or protection in the MPLS TP case. And it is also extended to carry some of the remote defects like RDI and AIS and those kind of things. And it is definitely a very, very useful protocol and useful mechanism which is deployed in MPLS networks. So this is what I was explaining. In ping, LSP ping and BFD, they are used in MPLS TP where IP is not present. So it uses a GAL-GASH mechanism. A specific label is identified to process the packet. And whenever that GAL label, which is the label 13, is present, the subsequent payload, which is called GASH, GAL-ACH, which will identify what type of payload it is, and based on that, it could be LSP ping payload or it could be BFD payload. And the payload is the same, it's only the header which is different, so everything else remains the same. So the extension for LSP ping and BFD was pretty seamless even for MPLS TP, where there is no IP present at all. So having said that, tools, most of the vendors and most of the third-party OEM tool providers have tools which involves all of these mechanisms, and even some of the Ethernet OEM tools, because you could see a lot of merge between metro and core networks, where, like, when you want to bring access, aggregation, and core into the mix, establish seamless MPLS, you need a common set of tool set all the way end to end. And by establishing one framework, you should be able to provide all these mechanisms like CV verification, CC verification, fault isolation, and supporting different type of FEC types. And the beauty of it is, once you actually got used to these tools, you will see that you really don't need much of the expertise, in the sense like I'm not saying that CCIs are not required, but in order to manage MPLS networks, you really don't need all of the intelligence to do small defect identification. You should be able to do some preliminary investigation as much as you can using these tools. Once after those things are available, you could actually use your expertise to go and figure out how to rectify the problem. But these tool sets or these mechanisms actually provide you much advantage, so that you could actually fix some of these problems in much shorter span than you used to, because in many cases you may not even have access to some of the core devices and the information on the configuration details and all those things on those devices. So summary of OEM tools. This is a simple table which I have put. Things could change. This is not a static. A lot of things have changed even when I first started trying to populate this table. So IPPM is one of the mechanism, but not many tools in MPLS uses, because MPLS TP has already defined some of the metric mechanisms to be done in MPLS networks. So yeah, this is just a top level picture. So in summary, MPLS OAM covers almost all of the MPLS networks as of now, and really to manage the idea of just CCIs is not a thing, but everyone should be able to use it. So, and you could check on your device CLIs or your EMS, NMS softwares. Most of the things are already present. So start using it. There's no harm. It's not going to bring down the network. After all, this is an OEM tool set. It may provide saying that, oh, I cannot do that or something, but that's pretty much it could do. And this is OEM package, so it should never ever bring down a device. And majority of the customers actually, or vendors, support these technologies. And there were many interrops, even I participated, which uses different vendor devices to verify these things, and pretty much every device actually works. And MPLS TP is also good technology. We have done quite a few interop sessions, and things work as well, but there's a lot of things which are evolving. Maybe in a matter of a year or two, things will solidify there as well. That concludes my tutorial. Have any questions? Well, if not now, feel free to ask me. I'll be in the conference, so any time of your choice, any questions. If you need to email me, feel free to email as well. And these slides are present, they're available in the NANOG site, so feel free to download.